It's Paul again, ready to show you how to use the techniques for finding eigenvectors and eigenvalues that you now know to do what's called diagonalizing a matrix and to raise a matrix to as high a power as you like with very little computation. I'm assuming you've already read through subtopic 1.6 of the executive summary. We're going to load up the practical math library to do our row reduction for us and pick a matrix that will turn out to have two eigenvalues, both integers conveniently, and therefore a basis of eigenvectors. As W, I will use the first standard basis vector. I'll make the matrix T in the usual way by multiplying once and twice by A. I will row reduce it, look at the result, and I can read off from that A squared minus 5 times A plus 6 times I acting on W is 0. That factors very nicely into A minus 2I times A minus 3I. Using A minus 3I, I get the eigenvector with eigenvalue 2. And using A minus 3I, I get the eigenvector with eigenvalue 3. Now I'm going to create a matrix. For consistency with the notation in the textbook, I am always going to call this P, and at some point we'll start referring to it as a change of basis matrix, but we haven't done change of basis formally. We're going to put that off till the start of next term when we do it for abstract vector spaces. Remember, an eigenvector is specified only up to a scalar multiple. So one thing we can do is choose both the eigenvectors to have a first component of 1. With some appropriate sign changes, we can make them equal 1, 1 and 1, 2 respectively. If we were doing hand computation, this would be especially nice because this matrix has a determinant of 1 and we won't get fractions when we invert it. In R, that's really not an issue. Now let's check that the matrix A does the right thing to this matrix. Its two columns are the eigenvectors, and A therefore multiplies the first column by the eigenvalue 2 and the second by the eigenvalue 3. That works. To proceed any further, we have to calculate the inverse matrix. Remember, P converted the standard basis vectors to eigenvectors. Its inverse matrix converts each eigenvector back to a standard basis vector. And therefore, when I multiply by P inverse, I get 2 times the first standard basis vector, 3 times the second standard basis vector. In other words, this product, P inverse times A times P, is a diagonal matrix whose entries are the eigenvalues. Let's look at this again by doing it step by step on a single standard basis vector. Then it's really going to be obvious. So let's start with the first standard basis vector. P turns that into the eigenvector for eigenvalue 2. Multiplying by A turns it into twice what we had before. And multiplying by P inverse, since we now have twice the eigenvector, turns it back into the eigenvalue times the second standard basis vector. Usually what we want to do is to express A in terms of P and the diagonal matrix D. So solving the equation D equals P inverse times A times P for A, we get A equals P inverse times D times P inverse. And sure enough, that's the matrix A we started with. This is normally referred to as diagonalizing the matrix, writing an arbitrary matrix as a product of 3 matrices, the last of which is the inverse of the first, and the middle one of which is diagonal. And the technique will work with matrices of any size as long as we find a basis of real eigenvectors. So let's try it on another familiar example from the preceding script. Here is a 3 by 3 matrix for which we found a basis of eigenvectors. There was one eigenvector with eigenvalue 1, and then we found from 2 different starting points 2 independent eigenvectors with eigenvalue 2. I will put those three together into a matrix P, and I will make a diagonal matrix whose entries are the corresponding eigenvalues 1, 2, and 2. I will use solve to invert P inverse, and when I multiply P by D by P inverse, I get back the matrix A. So we can do this. What's it good for? Well, the simplest application is raising a matrix to a power. If we wanted to raise the matrix A to the fifth power, we could do 4 matrix multiplications, but here's a much easier way. Let's raise the matrix D, which is diagonal, to the fifth power. All I have to do is create a matrix D5 where the diagonal entries are the fifth powers of the eigenvalues 1, 2, and 2, and R does that very naturally, since the fifth power can be applied to the matrix that gets built into the diagonal matrix. Now, this takes a little bit of inductive proof, but it will be easy to show that when I take PD P inverse and raise it to the fifth power, I get lots of cancellations, and the result is just 1 P on the left, 1 P inverse on the right, and the fifth power of D in the middle. That's the result of that calculation. And here's the result of raising A to the fifth power directly. That doesn't prove this always works, but it shows in a fairly general-looking example that is the case. A cuter stunt would be to find a cube root of this matrix. How are we going to do that? Well, all we have to do is to raise the eigenvalues to the 1/3 power, making a matrix D cube, whose third power is my original D. And now the same argument works. It works for any power. The cube root of A, which I'll call A cubed, is just P times this diagonal matrix D cubed times P inverse. There's the matrix. Nobody said its entries were going to be integers. I can calculate its cube directly, and what do you know? That's the matrix that we started with. So far, so good. If we have a basis of eigenvectors and they're real, we can always diagonalize the matrix. But what if the eigenvalues are complex? If you start with a problem involving nothing but real numbers, and you're going to end up with a solution involving nothing but real numbers, it's kind of a shame to have to introduce complex numbers in the middle of the calculation. And here's a way around that. This is not particularly well known. In fact, the only reference I can cite on it is Bamberg and Sternberg, a course on mathematics for students of physics, which I wrote about 30 years ago. We'll start with a matrix A that's going to turn out to have complex eigenvalues. We need to provide a little help to R, which can't do computer algebra, in calculating the characteristic polynomial. So look down there at that matrix, subtract T along the diagonal, do the multiplication, and you get the characteristic polynomial 3 minus T times minus 1 minus T plus 8, and that simplifies to T squared minus 2T plus 5. Setting that equal to 0, we find two roots that are going to be the eigenvalues, and they're 1 plus 2i and 1 minus 2i. You can get that, for example, by using the quadratic formula. But we already know a matrix that behaves like 1 plus 2i. It's the conformal matrix, where the first column is 1, 2. So there's our conformal matrix C. And what you can do in this case is find a matrix P that has real columns. These are not eigenvectors. They're just conveniently chosen in such a way that A is written as P times C times P inverse. Here's the way to do it. You can always choose the first column to be the first standard basis vector. Now we got that fixed up. The rule for the second one is a little bit tricky, and the proof of it is in the executive summary. The rule for constructing P2 is take the matrix A, subtract off the real part of this complex eigenvalue times the identity matrix, and then divide by the imaginary part of the complex eigenvalue. Here I'm just going to convince you that that works. So we put P1 and P2 together to make the matrix P. We invert it using the solve function. We compute P times the conformal matrix times P inverse, and we have reconstructed our matrix A. Why is this useful? Well, why is diagonalization useful? Because a diagonal matrix is easy to raise to any power. So is a conformal matrix. One way of looking at it is to say a conformal matrix is a stretching combined with a rotation. If we raise it to a power, we raise the stretching factor to the same power, and we multiply the rotation angle by the power. Equivalently, the conformal matrix C corresponds to a complex number Z, in this case Z plus 2i. R is happy to do complex arithmetic and raise it to the fifth power, and we can convert that fifth power, 41 minus 38i, to the conformal matrix that represents it, and now we have the fifth power of A, P times C5 times P inverse. There it is, and there's what we get by lots and lots of multiplication to raise A to the fifth power, the same number. Notice that this wouldn't have been significantly more difficult if we had wanted to raise A to the 1,000th power, or if we had wanted to extract a 10th root of the matrix A. So, this technique is sort of equivalent to diagonalization. Diagonalization simplifies the problem to raising a few numbers to a power plus some multiplication. This simplifies to raising a single complex number to the power combined with some matrix multiplication. This does not extend straightforwardly, however, to matrices that are bigger than 2 by 2. Now the last case. What if there is no eigenbasis? Is there anything we can do there? And here's the case from the very first script where we saw this phenomenon. This matrix A has a characteristic equation T minus 4 squared, and when we search for eigenvalues, we get the polynomial T minus 4 squared. So there it is. The eigenvalue is 4. A minus 4i squared is the zero matrix. That means the matrix A minus 4i has the curious property that one of its powers is the zero matrix. Such a matrix is called a nilpotent matrix, and the way you get a 2 by 2 nilpotent matrix is to have the image and the kernel be the same subspace of R2. The first application of the nilpotent matrix maps every vector into something on a line along the direction of the vector that's the kernel, along the direction of the image, and then because the image is the kernel, the second application smashes that whole line down into the origin. So n is A minus 4 times I, and its square is 0. But that also means that A is 4 times I plus a nilpotent matrix. That's what it looks like. Now suppose we want to raise this to the 5th power. Well, it's the sum of two terms raised to the 5th power, and since the identity matrix commutes with anything, we can use the same rules that apply in ordinary algebra, the binomial theorem. But there are no terms involving n squared, n cubed, and so on, because all those quantities are 0. So there are only two terms. The first one is the 5th power of 4 times the identity matrix. That's the 5th power of 4 times the identity matrix. And the second term has a coefficient of 5, and then I have to multiply by 1 power of 4 times I, and I have to multiply by n. So I have 5 times 4 to the 4th from raising 4i to the 4th power times n. Those two terms are the whole story. There is the 5th power of a. There is a check on it by direct calculation. And in general, in the case where you fail to find a basis of eigenvectors, you will always be able to use this nilpotent matrix trick. If you push this to its extreme, you will end up with something called Jordan canonical form, but that goes well beyond the scope of this course.